A sheet of dusty ice sits beneath the Martian surface, out of the worst sunlight, but not beyond every reach of warmth. And the question is simple: could life be hiding under Mars' ice today? The surface we know best is also one of the hardest places for living cells to survive. It is exposed to radiation, it is dry, its air is too thin for ordinary liquid water to last. But ice changes everything. It can shield, it can preserve. In rare settings, dust inside it may absorb sunlight and warm a thin hidden layer. By the end of this video, you will understand the narrow physical conditions under which Mars' ice could shelter life, and why proving it would be harder than finding the ice itself. So tonight we follow the line between a possible habitat and a real discovery. Not a hidden civilization, not a confirmed biosphere, a serious test of habitability and of whether we can read the evidence without ruining it. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. Start with the place our machines know best, the ground itself. The surface has the obvious advantages. It is visible from orbit. Landers can reach it. Rover wheels can cross it under the sun. If modern Mars were gentle, this is where the search would feel simplest. A cell would not need a drill, a hidden crack, or a buried layer. It could simply endure the world we can already see, but the visible world is exactly where Mars is least forgiving. Sunlight is not gentle there. Ultraviolet light reaches the ground almost unfiltered. Radiation works more slowly, breaking chemistry over time. Then the dry, oxidizing soil turns small injuries into a constant repair debt. The surface gives us access, then asks biology to survive without the protection and repair budget that access has stripped away. The open surface is where Mars has taught us the most, but also where modern survival looks worst. Ultraviolet light reaches the ground with little atmospheric shielding. Radiation slowly breaks delicate chemistry. The dry, oxidizing soil then makes every small injury harder to repair. The point is not a catalogue of punishments. It is that the ground itself keeps biology in debt. A dormant spore might survive better than an active cell. A buried organic molecule might last better than one exposed in dust. But active life on the open ground must face damage from several directions at once. The problem is not one killer condition, it's the combination. Begin with the rover's eye view, because it is the view that makes Mars feel closest. Wheels cross dust. Cameras inspect pebbles. A drill bites into rock. Nothing about that scene looks impossible. It looks reachable. Now put a living cell into the same scene and the meaning changes. The thin atmosphere lets harsh ultraviolet light reach the ground. Radiation keeps adding slower molecular damage. Dry, oxidizing soil makes repair harder just when water is least available. A camera sees a landscape. A cell meets a balance sheet it cannot easily pay, so the surface does not fail because one condition is dramatic. It fails because the penalties arrive together. A dormant spore might wait out some punishment. A molecule buried quickly might persist as a trace. But active life needs cycles of damage and repair, not damage without a workable repair window. That distinction keeps the argument grounded. The surface can preserve clues about ancient Mars. It can record minerals and salts. It can also preserve the scars of radiation and old water. It can even guide us toward better sites. But as a modern refuge, it starts near the bottom of the ranking because access is almost the only thing it gives generously. If a surface site deserves attention, it will be because some local feature changes the balance. A rock overhang can cut exposure. Buried ice can change the water question. A recent scarp can reveal material before the surface has fully rewritten it. The point is not the feature by itself. It is whether the feature reduces punishment without sealing away every source of water and energy. The surface teaches us the first rule. Reachability is not habitability. One more thing matters here. Surface hostility is cumulative. A cell does not meet ultraviolet light in isolation, then cold in isolation, then oxidants in isolation. It meets them together in a place where repair is hard because water is scarce and metabolism is slow. Damage can build faster than life can respond. The same point is also why ancient Mars and modern Mars must stay separate in our minds. Ancient riverbeds, lake sediments, and clay minerals tell us that Mars once had more generous environments. They make the life question stronger historically. But a lake bed from billions of years ago is not the same as a refuge for living cells today. A fossil search and an extant life search overlap, but they are not identical. If we forget that, the surface becomes a stage for the wrong story. We see sedimentary rocks and imagine modern biology. We see frost and imagine liquid habitats. We see rover tracks and feel close to the answer. But closeness is an engineering fact. Habitability is an environmental fact. Mars lets those two facts point in opposite directions. So the surface is not useless. Far from it. It holds context. It holds mineral evidence. It records climate. It tells us where water once moved. It tells us what oxidants and salts are doing now. But for living cells exposed today, it is the baseline problem every better hiding place must improve upon. So the open surface leaves us with a baseline, not a verdict. It tells us what any better refuge must escape. Radiation is part of it. Dryness is part of it. But the real test is whether a place gives damaged chemistry a chance to repair. The next candidate must improve more than one condition at once, because Mars punishes simple answers. Look at the surface as an experiment that has been running for billions of years. The instruments are not glassware and wires. They are the Martian sky, the dry soil and time. Every exposed rock and patch of dust has been sitting inside that experiment. Some materials survive it. Living chemistry has a harder time because the experiment does not pause when repair is needed. A cell can tolerate harshness when harshness arrives in pulses. Dry out, then rehydrate. Freeze, then thaw. Take radiation damage, then repair. On Earth, even extreme places usually offer some rhythm like that. A desert receives fog or rare rain. An icy surface has pressure and an atmosphere. A salty lake may be brutal, but it remains connected to a biosphere that keeps feeding it organisms and chemistry. Mars gives fewer recovery windows. Thin air reduces shielding. Low pressure makes ordinary liquid water unstable. Cold slows repair until small injuries can become permanent. Radiation does not need to erase everything at once. It can work slowly, breaking bonds and degrading molecules over long exposure ages. That is why a shallow scrape can tell a very different story from fresh material exposed by a scarp, a recent impact or a drill. That's why rover success can mislead the imagination. We can operate machines on Mars far more easily than a cell can operate itself there. A rover can carry batteries and heaters. It can seal its electronics and wait for commands from Earth. Biology would need the environment to provide its own repair budget. Water would have to appear when repair was possible. Energy would have to be usable rather than merely present. And the surrounding chemistry would have to leave delicate cellular machinery intact long enough for life to do anything with that chance. None of this makes Mars boring. It makes the search sharper. The open surface becomes the control case. If a proposed refuge does not improve on surface radiation, surface dryness, and surface chemical damage, then it is not a refuge. If it improves those conditions but loses all energy or water, then it has only moved the problem, so the surface gives us the first serious filter. It separates places that are easy to touch from places that might be worth touching. It also keeps the ancient life question in its proper lane. Ancient lake beds may be wonderful places to search for past habitability or preserved biosignatures. They do not automatically tell us where a living cell could persist now. That separation matters all the way through the film. Mars once had rivers and lakes. Groundwater moved too, during intervals that were more forgiving than today. Modern Mars is the narrower question. It's not asking whether the planet was ever habitable. It's asking whether any present environment still leaves enough shelter and activity for life to remain more than a fossil possibility. One quiet detail makes the surface especially severe. Mars does not need to kill a cell instantly to make life unlikely. Slow damage is enough. A strand of DNA can be broken by radiation. A membrane can dry out. A useful molecule can be oxidized. A repair system can stall because liquid water is not present long enough. Biology can tolerate punishment when it has time, water, and energy to repair itself. On the open Martian ground, those repairs become the hard part, but the surface still tells us where to go next. Dust can become cover. Fresh scarps can reveal material before the open air has fully altered it. Water-bearing minerals can record history without pretending to be living habitats. Surface Mars gives us context, not comfort. It sketches the damage pattern. Then it points below the damage. A useful way to hold the surface is as a map of insults. Where radiation is strongest, cover starts to matter. Where dryness dominates, stable ice becomes more interesting. Where oxidants have worked for too long, fresh or protected material carries more meaning. The surface is the problem statement written across the planet. That's why surface missions still matter for an under-ice question. They measure the punishment, they identify salts, they reveal minerals formed with water, they show how dust moves, how frost appears, how radiation and chemistry shape exposed material. They do not have to find living cells in the open to guide a better search. So the first ranking is almost paradoxical. The surface is least promising as a modern habitat, but it is essential as evidence. It tells us what any hidden refuge must be hidden from. That makes the surface more than a failed candidate. It becomes the measuring stick for the rest of the film. Each later refuge has to answer the surface in its own way. Dusty ice answers radiation with partial shielding. Buried ice answers exposure with cover. Brines answer freezing with salts. Deep rock answers ultraviolet light with distance. Planetary protection answers our own interference with restraint. The surface also keeps the story emotionally honest. Mars does not need monsters to be hostile. It does not need dramatic music to make survival difficult. The quiet combination of dryness and cold, then chemistry and radiation on top. And time is enough. For a cell, a calm-looking plain can be more dangerous than a violent-looking landscape, because the damage is constant and repair is starved. Now keep one thing in view as we leave the surface. We are not saying no cell could ever survive a brief exposure there. Microbes on Earth can be astonishingly tough. Some tolerate cold, some tolerate dryness, some survive radiation for a while, but survival for a while is not the same as living there. We need a place where damage can be repaired, where chemistry can keep running, and where water appears in a form biology can actually use. So the surface teaches us the first rule of the search. Mars life, if it exists now, probably needs a roof. Not a dramatic cave, not a hidden city, just enough material between the cell and the sky to change the physics. Now this helps us avoid a common mistake. A rover image can make Mars feel familiar because rocks and dust are easy for the human eye to read, but biology does not experience a landscape the way a camera does. A cell experiences chemical stress. It experiences broken molecules. It experiences water leaving faster than repair can keep up. So the surface is not rejected because it looks barren. It is rejected because its physics keeps pushing life away from activity. So when the search moves downward, it is not escaping into fantasy. It's following the physics away from the most damaging environment we can easily reach. The next clue is not speculation. Mars really does have ice. That matters because the popular image of Mars as simply dry is too crude. The planet is dry in the open-air sense, but not empty of water. Ice sits in polar caps. It hides in shallow ground at some latitudes. Orbiters have also mapped buried ice beneath dusty surfaces. For a life question, this changes the terrain from fantasy to a physical search area. Still, ice is only the beginning of the argument. Frozen water can preserve without feeding anything. It can shield without melting. It can sit close enough to see and still be too cold, too stable, or too chemically limited to act as a habitat today. Mars is not dry in the simple way people often imagine. The evidence is physical. Polar caps hold vast stores of ice. Mid-latitude ground can hide ice beneath a dusty cover. Bright scarps sometimes expose it directly to orbiting cameras. The planet is dry at the open surface, but it is not empty of water. That matters because ice changes the search from fantasy into geography. We can map it. We can compare latitudes. We can ask which deposits are stable and which are exposed. Then we can ask the harder mission question: which ones could actually be reached without destroying the story they hold? Now the word ice has to become specific. Mars ice is not one thing sitting in one place. Polar ice gives scale. Buried mid-latitude ice gives protection. Fresh scarps give access before exposure has fully rewritten the material. Those differences matter because each deposit tells a different story about reachability, shelter, and time. Polar ice gives scale and climate memory. Buried ice gives protection. Exposed scarps give access and fresh surfaces. Shallow ground ice gives a possible target for future drills. But none of those categories automatically gives a habitat. Frozen water can preserve evidence while remaining biologically silent. So the useful question is geographical before it is biological. Where is the ice stable? How recently has it been exposed? How much dust or debris covers it? Is it clean enough to transmit light or dirty enough to absorb heat? Is it close enough to the surface for sampling or protected enough to avoid radiation damage? A map of ice is only the first page of a habitability map. Here is where the title becomes serious instead of speculative. We are not inventing a hiding place. Mars has real ice to test. But a deposit only matters for life if it changes the balance that ruins the surface. It has to shelter the chemistry, offer water in a usable moment, and still leave a signal a mission could prove. So Mars ice matters because it gives the question an address. It tells us the search is not just a fantasy about an underground world. The problem is that an address is not a biosphere. A frozen archive may be precious even if it has never supported a living cell. Mars has enough ice to make the question real, but ice alone does not answer it. The important shift is from romance to mapping. Ice on Mars is not a vague white glow near the poles. Orbital instruments and radar contribute one part of the map. Thermal behavior adds another. So do landforms and exposed scarps. Together, we get pieces of a real distribution. Some ice is obvious, some is buried, some is protected by dust and debris. Some is too cold, too deep, or too unstable to help much. That distribution matters because life, if present, would not care about the planet in general. It would care about a site. Latitude matters because climate changes with latitude. Depth matters because shielding and light change with centimeters. Dust matters because it rewrites the energy budget. Habitability is local. Mars may be globally hostile and locally less hostile at the same time. But water ice can also mislead us because it preserves the feeling of water without the behavior of water. Frozen water does not feed a cell by itself. It may protect molecules. It may trap gases. It may preserve climate layers. It may become liquid briefly under special conditions. But until it moves or melts, it is mostly a frozen archive. It has to exchange with its surroundings before it becomes part of a living question. Here is why ice alone does not answer the title. It legitimizes the title. It tells us the hiding place is physically available. Then it forces the next question: which ice, under what conditions, and for how long? So the ice map narrows the search without ending it. Each deposit becomes a question about history. How deeply was it buried? How recently did the air touch it? How much dust sits inside the ice? Those details decide whether the deposit is only an archive or whether it ever becomes an active margin. The better the map becomes, the less useful it is to speak about Mars ice in the abstract. The real map of Martian ice is one of the reasons the under-ice question deserves patience. Orbiters have shown us forms that do not fit the old picture of Mars as simply dry. Radar can reveal buried structures. Cameras can catch scarps where bright ice appears beneath a thin cover. Thermal measurements can suggest where ground ice is stable. Landers have touched icy material directly in some settings. But the map is uneven because the planet is uneven. Ice stability depends on latitude and slope. Elevation matters too. So does the dusty cover above it, atmospheric exchange, and climate history. Mars has shifted its obliquity over time, moving ice and changing where deposits survive. A place that looks dry today may hide old ice. A bright exposure may be young, vulnerable, or actively retreating. A buried deposit may be stable for long periods while remaining physically inactive. That difference between stability and activity is central. Stable ice is good for preservation. It can hold layers, trap climate clues, and protect some molecules from immediate surface destruction. Active habitability asks for more. It asks whether water ever becomes available. It asks whether energy enters the system. Then it asks whether the whole setting lasts long enough for life to respond. A future mission would therefore care about more than finding ice. It would ask whether the deposit is old or freshly exposed. It would ask how dusty the ice is, because dust can both warm and darken the layer. It would read the nearby landforms for signs of recent movement. The same word, ice, could describe a dead archive, a useful shield, or a short-lived physical system where water briefly matters. This gives the search its progression. First, we reject the surface as the easy answer. Then we accept that Mars has real ice. Then we refuse to confuse real ice with living conditions. That refusal keeps the question in the evidence-led lane. The title asks whether life could be hiding under Mars ice. The honest path asks which ice, at which depth, with which physics. So Mars ice is not a reveal. It's an invitation to rank. The ranking therefore cannot reward ice in general. Polar caps may be magnificent climate archives. Mid-latitude buried ice may be more reachable and better shielded. Fresh scarps may briefly expose what is normally hidden. After that, the question turns from category to interpretation. Which deposit can preserve context, avoid surface damage, and still be tested cleanly? The strongest candidate will probably not be the most visually obvious one. It may be a dirty, local, awkward deposit where shielding and limited light overlap just long enough for water to matter. That's less cinematic than a global underground ocean, but it is much closer to the science we can actually test. The most useful ice on Mars may not be the most beautiful ice. A bright polar cap looks obvious from orbit, but an exposed mid-latitude scarp may tell a more testable story. A buried glacier under dusty debris may hold cleaner water ice than the landscape above suggests. A shallow ice table may shift with latitude and season. Each deposit carries a different history. Some were buried, some were exposed, some were lost and renewed by changing climate. So we do not ask whether Mars has ice in the abstract. We ask what kind of ice the mission would meet. Dust changes the light and heat. Depth changes protection and access. Exposure age changes how much the surface has already altered the sample. The word ice sounds simple, On Mars, it becomes an atlas of trade-offs. Think of that atlas as a set of possible mission choices. Exposed ice may be fresh enough to read, but the same exposure can alter it quickly. Buried ice may be better protected, but drilling becomes harder and light is lost. Dusty ice creates the most intriguing mechanism only within a narrow balance of dust, light, and water. Every attractive target spends something to gain something else. That's why a future life detection mission would probably not chase the prettiest ice. It would chase the most interpretable ice. The chosen site would need enough scientific promise to justify the risk, but also enough cleanliness and context to make a result meaningful. Now we can make the question sharper. Ice on Mars is not one thing. Some of it is obvious from orbit. Some of it is inferred from radar. Some sits close enough to the surface that fresh impacts and scarps can expose it, but we should not let the word water do too much work. Frozen water can preserve a clue for millions of years and still offer no living habitat today. So when we talk about Mars ice, we are really asking what kind of history the ice has. Depth tells us how protected it may be. Dust tells us how energy moves through it. Stability tells us whether anything could happen often enough to matter. The question is whether a frozen archive can ever become a living margin. Now, the mapping itself matters because it changes the search from fantasy into geography. We can point to polar deposits. We can point to mid-latitude ice. We can point to fresh exposures where bright material appears and then slowly changes as it meets the air. But a map of ice is not a map of life. It is a map of places where the first requirement has not vanished. Water is still present in solid form, and that lets us ask the harder questions with real coordinates instead of imagination. That makes the ice map less like a treasure map and more like a decision tree. Every branch asks what the ice has been through before we arrive. A deposit that survived quietly for a long time may be excellent for preservation and poor for present activity. A younger exposure may be easier to sample and harder to trust. That is why the search cannot simply reward the place that looks most accessible from orbit. It has to reward the place whose history can still be reconstructed after the spacecraft touches it. Dust changes ice from a passive archive into a possible machine. Imagine grains trapped inside blue-white ice on a red planet. They do not have to be alive to matter. Dark dust can absorb sunlight. Under specific conditions, that combination may create a small internal layer where light, shielding, and warmth overlap better than they do on bare ground. This is the doorway that makes the title serious, but it is not a shortcut to life. The same dust that warms can also block light. The same shallow depth that allows photosynthesis can expose chemistry to damage. Latitude and season squeeze the possibility. So do grain size and ice purity. Pressure, sublimation, and melt duration narrow it further. The dusty ice mechanism is the cleanest doorway into the title. In the 2024 Communications Earth and Environment paper, Aditya Kular and colleagues modeled how light moves through Martian snow and ice mixed with small amounts of dust. They were not claiming life exists. They were asking whether a radiatively habitable zone could exist inside exposed mid-latitude ice. The result is elegant because dust plays two roles. Dust absorbs sunlight much more strongly than clean ice. That can warm the ice locally. But dust also blocks light. A little dust can help create a useful layer. Too much dust can choke it off. In some model cases, radiatively habitable depths could sit within centimeters for dusty ice, and deeper for cleaner ice. The phrase sounds simple. The balance is not. Dusty ice earns its place because it changes two variables at once. Clean ice can let light travel, but it may also let damaging radiation reach too far. Dust can absorb sunlight and warm a local layer, but too much dust turns the ice opaque. The possible habitat lives between those failures. That's why the 2024 model is useful and limited at the same time. It gives us a physical doorway. Sunlight enters snow or ice. Dust grains absorb some of that energy, somewhere below the surface. A narrow depth may still keep useful light while reducing the worst ultraviolet damage. The model does not show microbes. It shows a possible overlap in the physics. The overlap is fragile. Latitude controls how much sunlight arrives. Dust content controls whether that light warms the layer or dies too quickly. Grain size and exposure history can then shift the useful depth enough to close the window. Water remains the final test because a radiatively habitable layer without liquid water is only a better lit freezer, so dusty ice should not be sold as a Martian oasis. Its strength is narrower and more interesting. It's one of the few near-surface mechanisms where protection and energy do not immediately cancel each other. Light may remain at one depth while radiation weakens at another. Dust may warm the layer until the same dust turns it dark. The doorway closes whenever that balance becomes too dry, too brief, or too hostile to use. Dirty ice is not proof of life. It is one of the few mechanisms worth taking seriously, worth being precise about the 2024 model. The paper did not send a camera under Mars ice. It used radiative transfer modeling to ask how ultraviolet and photosynthetically active radiation could move through snow, fern, and ice with Martian dust mixed in. It highlighted exposed mid-latitude ice because that is where present-day melting may be more plausible than at the poles. The modeled radiatively habitable zone is a balance between two kinds of light. Damaging ultraviolet radiation must fall below dangerous levels. Photosynthetically useful light must remain high enough to matter. Clean ice can transmit light deeper, but ultraviolet can penetrate too. Dust can block ultraviolet more effectively, but it also blocks the visible light biology would need. Here is why tiny percentages matter. The study discusses dust contents around the 0.1% by mass as enough to change penetration depths dramatically. In very dusty ice, the light dies too quickly. In cleaner ice, useful light can reach deeper, but the radiation problem is harder. The sweet spot is not a slogan, it's a model-sensitive layer, and even if the light math works, liquid water remains the hard condition. A radiatively habitable zone is not automatically wet. It's a zone where the radiation environment might permit photosynthesis if liquid water is available. That final phrase carries enormous weight. So dusty ice stays near the top of the trial for a specific reason. It does not promise life. It offers a physical compromise that can be modeled, mapped, and eventually tested. The compromise is simple to picture: partial shielding, enough light to matter, and the unresolved question of whether water ever becomes usable. Picture a small amount of dark dust inside pale ice. On Earth, that detail can matter enormously. Dark grains absorb sunlight, warm the surrounding ice, and help create little melt features. Those features can become microbial habitats because Earth supplies the generous background Mars lacks: pressure, repeated wetting, and a biosphere already ready to occupy the opening. Mars takes the same mechanism and removes the generosity. The dust can still absorb sunlight. The ice can still scatter and transmit light. A shallow layer can still reduce damaging ultraviolet radiation, but the pressure is low and the cold makes every wet moment fragile. Any liquid water may arrive as a brief salty event rather than a stable habitat. The analogy opens the door, then Mars narrows the doorway. That narrowing is exactly why dusty ice is better than a vague underground life idea. It creates measurable questions. Dust content and grain size tell us how light moves. Latitude tells us how much energy arrives. The hard final question is whether any melt can persist before freezing, evaporating, or migrating away. The 2024 modeling work is useful because it gives those questions a physical frame. A radiatively habitable zone is not a hidden pond. It's a layer where harmful radiation may be reduced while photosynthetically useful light remains. The phrase sounds biological, but the model itself is about radiation and light. Biology enters only after water, chemistry, and duration are dealt with, so the scientific value lies in the overlap, not in a claim of discovery. A dusty layer may be shallow enough to receive energy and deep enough to gain partial protection. It may warm internally because dust absorbs sunlight, but the same candidate can fail if water never becomes usable, if sublimation removes the ice, or if the liquid appears only as a hostile moment rather than a sustained environment. This gives dusty ice a special place in the ranking. It's not the strongest proof candidate. It's not the broadest possible habitat. It's the clearest mechanism linking the title to present-day Mars physics. The viewer can understand why ice and dust matter. Depth matters too, but the answer remains bounded, because every helpful condition brings a limit with it. A serious mission would not arrive looking for tiny green organisms in a blue cave. It would arrive with a model, a clean sampling path, and instruments designed to doubt their own first result. First, it would ask whether the modeled layer exists at the site. Then it would ask whether water activity ever crosses a useful threshold. Only after that would any possible signal get tested against competing explanations. That's why dusty ice belongs near the center of the film. It lets us ask a hopeful question without lying about the answer. The cryoconite analogy helps if we keep it on a leash. On Earth, dark particles on ice can absorb sunlight and make little melt holes. Microbes can use those pockets because Earth supplies pressure and atmosphere. It also supplies repeated wetting on a planet already saturated with life. Mars lacks that generous background. The analogy shows a mechanism, not a verdict. Still, the mechanism has real force. Dust inside ice is not just dirt. It changes the flow of energy. It can let light enter, absorb some of that light, and warm a small region below the surface. The promise lives in that small region. The danger lives there too, because the same dust can cut off light, drive sublimation, or leave water too brief to matter. The phrase photosynthesis also needs caution. If a Martian organism existed, we do not know that it would use photosynthesis. The dusty ice model matters because photosynthesis gives a measurable light requirement, not because it proves the kind of life that would be there. It lets scientists ask whether a known biological strategy has any physical room on modern Mars. Even that room would be conditional. Useful light is not food by itself. A cell would still need liquid water. It would need nutrients and manageable salts. Above all, it would need time. If melt happens only briefly, the system might be more like an occasional chemical event than a habitat. If melt happens repeatedly but leaves an extreme brine, water activity may still fail. So dusty ice should be heard as a serious maybe, with the stress on serious and maybe equally. Now imagine ranking two dusty ice sites. One has cleaner ice, so useful light travels deeper, but ultraviolet may also penetrate farther. Another has more dust, so radiation drops faster and heat is absorbed more strongly, but photosynthetic light dies quickly. A site can look better on a map, and still fail if it has been exposed too long, or if the modeled warm layer never becomes wet enough. None can be judged by appearance alone. Now this is where the dusty ice idea earns its place. It does not ask us to imagine a huge underground ocean. It asks us to imagine a thin physical compromise. We can picture light entering ice and fading with depth. We can picture dust grains absorbing some of that light. We can picture the upper ice acting as a shield, while the lower layer keeps a little warmth. But the elegance is also the warning. A mechanism can be real and still be rare. It can produce a possible niche without producing life. That distinction keeps the whole story honest. Now, a mission would have to test this doorway with restraint. It would measure the dust. It would measure the light. It would measure temperature through the ice, instead of assuming the surface tells the whole story. And then we would still need the hardest measurement, whether any water produced in that layer lasts long enough to matter. A brief thaw can change chemistry. A recurring wet zone can change the biological question. That's why this doorway remains scientific. It does not ask the viewer to believe in life. It asks the viewer to follow a balance that can fail in several measurable ways. The word under sounds simple until we measure it. Under ice sounds like one place, but depth splits it into different worlds. A thin cover may still feel the surface. A buried lens may gain protection while losing light. Far below that, sampling itself can become the dominant problem. Those are not versions of the same hiding place. They are different environments with different costs. The possible habitat is squeezed between two failures, too shallow, and the ice still belongs to the surface problem. Radiation can reach it, and the exposed layer can retreat before a stable niche forms. Too deep, and the world becomes dark, cold, and energetically poor. The most interesting layer may therefore be neither dramatic nor vast. It may be thin, local, and easy for both cameras and expectations to miss. Under ice is not a location, it's a measurement. 1 centimeter under ice is still near the violence of the surface. 1 meter under ice may be better shielded, but light may be fading. 10 meters changes the problem again. Kilometers change it completely. Here is why the narrow layer matters. Light has to reach far enough to matter, but not so far that radiation dominates. Cover has to be thick enough to protect, but not so thick that it starves the layer of energy. Every extra bit of depth helps one requirement and threatens another. The phrase under ice sounds protective, but protection has a depth. A centimeter can still belong to the surface. A meter may be shielded but dim. A buried glacier changes the question again. Each step downward buys shelter and spends something else. Near the top, the ice still belongs to the surface environment. Ultraviolet light can damage chemistry, and sublimation can strip the ice away before a stable niche forms. Move downward and the damage softens, but so does sunlight. Dust sharpens the trade-off. Enough can warm and shield, too much can turn the layer dark. The possible refuge lives inside that exchange, not outside it, so the habitat, if it exists, is not a room, it's a crossing. Radiation fades with depth. Useful light fades too. Somewhere between those two losses, warmth and chemistry may briefly create a usable margin. The interesting place is where those curves overlap, not where any single one looks promising by itself. That overlap may be local, seasonal, and fragile. It may exist in one slope and not another. It may shift after a dust storm. It may close when the ice texture changes or when exposure removes the top layer. A future mission would not simply ask whether ice is present. It would ask whether the right centimeters are present. The most interesting place may be neither surface nor deep cave, but a narrow band easy to miss. The narrow layer problem is also a language problem. Under ice sounds protective. It does not tell us whether the layer is protected enough. It does not tell us whether light remains. It does not tell us whether the ice texture lets energy move through it or traps the system in cold stillness. A few centimeters can be scientifically meaningful on Mars. That is not intuitive from Earth, where we often imagine habitats as broad places we can enter or scoop up. On Mars, a few centimeters can be the difference between lethal ultraviolet exposure and a filtered light field. A few more centimeters can be the difference between light and darkness. This makes the search visually modest but intellectually sharp. We are not always looking for a big blue reservoir. We may be looking for a boundary inside ice where two curves cross, radiation falling below one threshold and usable light staying above another. The habitat, if it exists, is the overlap. That overlap could shift with season and slope. A dust storm could change the surface cover enough to move the boundary. Ice texture could change it again. It may appear in one scarp and not another. It may be destroyed by exposure over time. Mars does not offer a neat layer labeled habitable. It offers conditions we have to reconstruct. So the narrow layer turns a romantic phrase into a measurement problem. The candidate habitat may be only a boundary, not a landscape. Its value depends on centimeters and textures. Dust fractions matter. Seasons matter too, in ways a headline would never bother to name. Depth is easy to say and hard to interpret. Under ice could mean a place still shaped by surface weather. It could mean a layer where radiation has weakened but light survives. Deeper down, the same phrase can describe a world where sunlight has vanished, and chemistry must carry the energy story by itself. For shallow ice, the danger is exposure. Ultraviolet light can penetrate enough to damage biology. Oxidants and surface chemistry can interact with the layer. Sublimation can remove ice or change its structure. Daily and seasonal temperature swings can make conditions unstable. A layer can look protected in a diagram and still be too close to the surface in practice. For deeper ice, the danger reverses. Radiation falls, but photons disappear. Temperatures may become steadier, but still too cold. Melt may require unusual local heating, salts, or geometry. Any life depending on sunlight would lose its energy source. Any life depending on chemistry would need the ice to connect to rock or salts. It would also need some moving exchange, through gases or water, that can provide usable gradients. So the best under-ice candidate is not simply as deep as possible. It's the depth that solves the most important damage problem without creating a worse energy problem. That's a much more precise idea than the title suggests. It turns under into a question of centimeters and meters. Then it becomes a question of texture and threshold. The narrowness also affects detection. If the useful layer is thin, a drill can miss it. If the layer changes with season, one visit can misread it. If exposure history matters, two nearby scarps can behave differently. If dust content changes across the ice, the radiative balance can shift over small distances. Mars can hide the answer not because it is mysterious in a supernatural sense, but because the tolerances are tight. Here is where the viewer should feel the scientific tension. A vast hidden biosphere is easy to imagine and hard to justify. A thin, protected layer is harder to romanticize but easier to test honestly. It gives the mission a target shape. Map the ice first. Model the light and radiation together. Then sample slowly enough that heat and contamination do not erase the answer. If the answer ever comes from under ice, it may come from a place that looks unimpressive at first glance. Not a cave mouth, not a lake shore, a boundary inside dirty ice where several hostile curves briefly fail to close the door. Under depth turns the whole question into a knife edge. Move upward and ultraviolet damage returns. Move downward and useful light fades. Dust can warm and shield the layer until it becomes too opaque. Then the larger point takes over. A possible refuge can vanish because the local texture, season, or exposure history changed by a little. That's why a map alone cannot settle the issue. The right site would need the right geometry. Ice exposed at the wrong angle may lose water. Ice buried under the wrong cover may never warm. Ice sitting in the right latitude may still miss the right texture. The hiding place, if it exists, may be less like a cave and more like a thin physical compromise. And narrow targets reward patience. A broad claim can survive on atmosphere for a while. A narrow claim has to survive measurement. It has to name the depth and the energy source. It has to explain the exposure history. It also has to show how Earth was kept out of the result. That's harder to sell in one sentence, but it is far more likely to age well. Careful language is not weaker here. It's the tool that keeps the science intact for every future mission. That compromise changes how we imagine exploration. A rover camera might see only a slope, a scarp, or a patch of pale material. The real target could sit beneath the visible surface, not far enough down to be dramatic, but far enough to change the radiation field. The mission would need to understand the site before disturbing it. Sampling strategy becomes part of the science. Drill too shallow and the sample may represent damage. Drill too deep and the sample may miss the light-linked zone entirely. Heat the ice too much and the chemistry changes. Mix layers and the depth story disappears. A narrow habitat demands narrow handling. Now the word under becomes dangerous. Under ice could mean just below a frosty skin. It could mean beneath a buried deposit. It could mean far below any light that could feed photosynthesis. So we have to treat depth as a measurement, not a mood. A few centimeters can matter. A few meters can change the energy source entirely. And once we do that, the title becomes more precise. We are not looking for a vague beneath. We are looking for a layer where the punishment from above has weakened, but the usable energy has not disappeared. Now this is why a beautiful cross-section image can be misleading if we let it become too simple. The possible layer is not a clean blue stripe waiting underground. It is a shifting boundary controlled by dust and season. Slope matters. Local climate matters too. We should expect patchiness. One site might close the window completely. Another nearby site might leave it barely open. The difference could be small enough to miss unless the mission is designed for the layer itself. Under dust, so the hardest part of under-ice Mars may be respecting small differences. On this planet, small differences can decide whether the answer remains possible. Buried glaciers offer a more substantial kind of shelter. Here, the appeal is easy to understand. A dusty surface can cover real ice. Radar and imaging can point to deposits that are protected from the worst surface exposure, yet not necessarily as remote as deep aquifers. If we are looking for a place that Mars has actually preserved, mid-latitude buried ice belongs near the center of the search. But preservation is not metabolism. Cover blocks radiation, and it also blocks light. Burial slows sublimation, and it can also lock water into cold stillness. A glacier-like deposit may be a superb archive of climate and chemistry while remaining a poor active habitat, unless some source of warmth, liquid water, and usable energy can reach it. Buried mid-latitude glaciers are powerful because they are not imaginary. Orbital mapping and landform studies point to ice hidden beneath protective debris in regions far from the poles. For exploration, that is tempting. It's closer than deep aquifers and less extreme than polar interiors. But buried ice is often an archive before it is a habitat. It can preserve climate history. It can preserve molecules. It may even preserve traces of past environments. Active life is a different claim. Cover protects the ice, but it also blocks sunlight and makes any melt harder to sustain. Buried glaciers look more promising because they solve the surface problem more convincingly. A debris blanket can reduce radiation and slow sublimation. It can soften temperature swings. Over long periods, it can help preserve the ice beneath. Compared with exposed ground, that is a major improvement. But the same cover that protects the deposit also changes its biology. Sunlight may be gone, exchange with the atmosphere may be limited, temperatures may remain too low for meaningful liquid water. The ice may become an archive, excellent for climate history, possible preservation, and ancient chemistry, but poor for active metabolism today. So the important places may be edges rather than interiors. A basal contact, a fracture, a salty interface, a place where ice touches rock, dust, or minerals that can still participate in chemistry. If a buried glacier matters for extant life, the question may not be whether the glacier itself is alive. It may be whether any boundary around it keeps water, energy, and chemistry in motion. Access adds another penalty. Buried mid-latitude ice may be more reachable than a deep aquifer, but drilling is still not a neutral act. The cleaner the sample we need, the more carefully we must enter. A protected deposit is attractive partly because it has been protected from the surface. Touching it badly can erase that advantage. Buried ice improves protection while making metabolism harder. Mid-latitude buried ice also has a practical pull. It sits in the imagination between two extremes. It isn't the exposed surface, where destruction is strongest. It isn't a deep invisible aquifer, where access becomes almost impossible. It feels like the kind of place a future mission might actually test. Here is why it appears again and again in exploration planning. Buried ice can matter for climate science and geology. It can also matter for astrobiology, even before anyone talks about resources. But for this documentary, the resource angle stays outside the frame. We care about ice as evidence and habitat, not as fuel. A debris layer can protect ice from sublimation and radiation, but the same debris can block sunlight and insulate the ice. It complicates the thermal story. It can force a mission to drill. If biology needs photosynthesis, burial is a problem. If biology can use chemistry, burial may help. The same ice deposit changes rank depending on the energy strategy imagined. So buried glaciers sit in the middle of our trial. They are more plausible than the naked surface for preservation and shielding. They are less straightforward than dusty exposed ice for light. They may be excellent archives. Whether they are active habitats is a tougher question. So buried glaciers remain serious but ambiguous. They are strong candidates for preservation and shielding. For active life, their best hope may sit at interfaces where ice, rock, salts, and occasional movement meet rather than in the quiet frozen center. Buried mid-latitude ice feels practical because it sits between extremes. It's not the exposed surface where damage is strongest. It's not a deep invisible reservoir where access becomes almost fantasy for current missions. It's close enough to imagine drilling and protected enough to take seriously. Radar and imaging studies make these deposits more than speculation. Mars has landforms that resemble debris-covered glaciers and ice-rich structures. Some deposits appear protected under rock and dust, preserving water ice at latitudes where exposed ice would not last. For a mission planner, that is compelling. The ice is real enough to map and may be reachable enough to sample. The biological question is more stubborn. Cover reduces radiation and sublimation, but it also removes sunlight. If the candidate life is photosynthetic, burial quickly becomes a problem. If the candidate life is chemical, then the question shifts to interfaces, ice against rock, salts mixed with dust, fractures, basal zones, or places where liquid films might form under special conditions. That's why the middle of a glacier may not be the most interesting place. A frozen interior can preserve a record for a long time without offering much active chemistry. The edges can be more dynamic. A contact zone can concentrate minerals. A fracture can move gases or brines. A dirty layer can absorb heat differently from cleaner ice. Small boundaries can matter more than the large frozen mass. Access complicates the ranking further. A drill into buried ice must pass through overlying material that may be chemically messy. It must avoid carrying contaminants downward. It must control heat so it does not create artificial melt or smear layers together. If the possible habitat depends on delicate chemistry, the sampling method can distort the evidence. So buried glaciers deserve respect, but not exaggeration. They improve protection better than exposed ice. They preserve better than the surface. They may provide some of the most reachable under-ice targets. But for modern life, their weakness is energy and activity. They may be excellent freezers of history rather than homes for biology now. That does not make them secondary in the film. It makes them the best example of Mars trading one requirement for another. The more protected a place becomes, the more we have to ask what keeps it alive, rather than merely intact. Buried glaciers are tempting because they feel substantial. They are not a passing frost. They are bodies of ice, often wrapped in debris. Old climate cycles may have shaped them. Some sit close enough to the surface that a future drill becomes imaginable. Protection looks much better here than on exposed ground. Preservation looks better too. but preservation can become the trap. A glacier can keep a record beautifully while offering little active chemistry. The debris blanket that saves ice from sublimation can block sunlight. The cold that preserves molecules can slow metabolism to almost nothing. If a buried glacier matters for modern life, the most important place may not be the middle of the ice. It may be an edge or a basal contact. It may be a fracture or a salty interface where chemistry can still move. The archive idea is powerful because it can produce real science even without living cells. Buried ice could preserve climate records and trapped dust. It might also hold old atmospheric signals or organics delivered from elsewhere. A negative life result from such a deposit would still matter if the environmental history were clear. It could show that protection and water ice were not enough under those conditions. But the active life question keeps pulling us to boundaries. Ice against basalt. Ice mixed with salts. Ice beneath a debris layer that changes thermal behavior. Ice near a fracture or slope that has exposed fresh material. Those boundaries are where energy and chemistry are more likely to change. Now, buried ice gives us a different kind of promise. It feels more protected. It feels more durable. It is easier to imagine evidence surviving there than on an exposed plain. But we have to ask, what is being protected? A buried glacier may protect old organics. It may preserve a climate record. It may hold a frozen memory of Mars changing over time. That is valuable even if nothing is alive. For modern life, though, we need more than preservation. We need a way for chemistry to keep moving inside or beside the ice. And now think about what a buried glacier does well. It removes the ice from direct sunlight. It slows sublimation. It keeps a record of older climates under a blanket of dust and broken rock. But the same blanket that protects the ice also separates it from easy energy. We cannot simply say shielded and stop there. We have to ask what reaches the buried layer after the surface has done its job too well. So buried ice sits in the middle of the ranking. Better than exposed ground for preservation, more real than a vague deep aquifer. But still not an easy place for active life unless another source of energy appears beside it. So buried glaciers are not a yes or no category. They are a family of micro-settings, and the margins may outrank the mass. Salt is where the Mars life story often gets too easy. The tempting line is simple. Salts lower freezing points. Mars has salts. Therefore, liquid water may appear where pure water cannot. That is true enough to open a door, but not strong enough to walk through it. For biology, the question is not whether something is liquid-like. The question is whether the water is usable. A brine can be too cold, too concentrated, too chemically stressful, too brief, or too dry in the water activity sense to support known life. Salt may keep water from freezing while making it less biologically available. This is why brines belong in the center of the film, not as a footnote or a headline shortcut. Brines are the great shortcut in Mars storytelling. Add salts, lower the freezing point, and suddenly liquid water seems possible. Perchlorates and chlorides matter for exactly that reason. They change how water behaves in the cold, but the recent brine literature is a necessary break. Liquid is not enough. Biology cares about water activity, how available that water is for cells. A brine can be liquid and still be too cold. It can be too salty, too chemically stressful, or simply too short-lived for known organisms. The Penayes paper on the elusive nature of Martian liquid brines is important because it pushes against the easy phrase, water equals life. Brines deserve their own trial because they expose one of the easiest mistakes in Mars storytelling. Salts can lower the freezing point of water. Mars has salts. Therefore, liquid-like water may appear under conditions that pure water could not survive. Every step in that sentence can be true, and the conclusion can still disappoint biology. A cell does not need the word liquid, it needs usable water. Water activity measures how available that water is for life. In a very salty brine, water can be present while being hard for cells to use. The chemistry that prevents freezing can also create stress. The temperature that permits the brine may be so low that metabolism slows toward uselessness. The wet interval may be too brief to become an environment rather than an event. That's why brines are not just a caveat. They are a correction to the entire instinct that water equals life. On Earth, the shortcut often works because liquid water sits inside a generous biosphere. On Mars, liquid-like water may appear at the edge of known biological limits. With salts, cold, radiation history, and short duration all pushing the other way, so a brine rises in the ranking only if it remains biologically available, not merely physically liquid. It has to last, it has to stay warm enough, and it has to avoid intolerable chemistry while connecting to an energy source. Without those conditions, the brine is a chemical curiosity, not a refuge. On Mars, liquid water can be chemically real and biologically disappointing. The brine trap is powerful because it exploits a true statement. Salts really can lower the freezing point of water. Mars really has salts, including perchlorates. Thin films or metastable liquids may be possible under some conditions. None of that is fake. The error comes when a true physical statement becomes a biological shortcut. Life does not use the word liquid the way headlines do. Cells care about water that can participate in metabolism. If salts bind water too strongly, the water may be present but not available. If temperatures are too low, chemistry slows toward uselessness. If the liquid lasts briefly, a stable ecology becomes harder to imagine. Here is why brines deserve more than a passing caveat. They are the easiest way to make Mars sound more habitable than it is. They are also one of the best ways to teach the viewer the difference between water as a molecule and water as a biological resource. A good Mars life search must be able to say something counterintuitive. The presence of liquid-like water can sometimes reduce habitability if the chemistry that keeps it liquid makes it hostile. Mars keeps doing this. It gives with one hand and takes with the other. So brines move through the trial as both temptation and warning. They rescue liquid water from freezing, then ask whether the rescued liquid is actually usable. That correction is one of the most important safeguards against Mars life hype. The brine problem is useful because it forces precision into the most abused phrase in astrobiology. Follow the water is a good search strategy only when water remains biologically meaningful. On Mars, salts can make water physically present while pushing it beyond what known cells can use. Perchlorates and chlorides lower freezing points. They can allow liquid or liquid-like phases at temperatures where pure water would be ice. That sounds like a rescue, but cells do not experience a brine as a headline. They experience osmotic stress, low water activity, extreme cold, chemical reactivity, and the duration of the wet state. A liquid that exists for a short nighttime interval may not be a habitat. A liquid that holds water too tightly may not help metabolism. A liquid that is cold enough to preserve molecules may also slow chemistry almost to a halt. That's why brines can rank lower than intuition expects. They solve the freezing problem by changing the chemical problem. They give Mars a way to make wetness, then ask whether wetness has become biologically hostile. A beautiful phase diagram can still describe a poor ecosystem. The best version of the brine case would involve more than salts. It would need a protected setting, recurring availability, tolerable water activity, manageable chemistry, and an energy source. It would need enough time for biology to do something, not merely enough time for an instrument to say liquid. It would need a context where a possible biosignature is not immediately explained by abiotic salt chemistry. Brines also matter for evidence because they can alter molecules. They can move them. In the wrong setting, they can concentrate or destroy the signal we hoped to read. They can help create chemical patterns that look interesting without being biological. They can preserve some things and degrade others. They can make the sample more complex even when they do not make the habitat more livable. So the brine trial is not pessimism for its own sake. It's the correction that makes the final answer trustworthy. Mars may have liquid-like water in special circumstances. The responsible question is whether that liquid is usable, stable, warm enough, chemically tolerable, and connected to energy. A future instrument might detect salts, water-related minerals, or a chemical change that points to brine activity. The careful response would not be disappointment, it would be a better question. Did that brine exist at temperatures compatible with known life? Did it last long enough? Was the water activity above biological limits? Did it contact organics, minerals, or energy sources in a way that could support metabolism? Could the same chemistry be produced without life? Those questions turn a tempting signal into a usable investigation. They also protect the under ice promise from becoming a Water on Mars rerun. Once that question is asked, the easy slogan disappears. What remains is stronger because it can survive scrutiny. Brines also force a deeper distinction between survival and growth. Some organisms can endure extreme conditions in inactive states. Endurance is not the same as a functioning habitat. A cell trapped in a hostile brine may persist for a while without dividing, repairing well, or exchanging enough material to become an ecosystem. For modern Mars, that distinction matters. A search for living cells would need to know whether the environment can support activity, not only whether biology could briefly tolerate contact. Mars may offer many moments that are interesting chemically and very few that are generous biologically. Brines teach the most important Mars life correction. Liquid is not enough. On Earth, liquid water feels nearly synonymous with opportunity because biology surrounds it. Mars forces a harsher vocabulary. Water activity measures how available water is to cells. Salt chemistry changes stress. Temperature changes reaction rates. Duration decides whether a wet event is a habitat or only a flash. Perchlorates and chlorides can keep water liquid at lower temperatures, which sounds like a gift. The gift comes wrapped in penalties. The liquid may be extremely cold. It may pull water out of cells rather than support them. It may exist in thin films or brief nighttime windows. A brine can be chemically real and biologically disappointing at the same time. There's another trap in brine language. A transient liquid can make a spectacular measurement without making a stable world. Instruments may detect chemistry that proves water moved, salts dissolved, or a thin film appeared. That would be important. It would not automatically mean a cell had enough time to maintain itself and repair damage. It would still need exchange. It would still need the conditions for reproduction. Biology has thresholds. Below certain water activities, known organisms cannot function. At very low temperatures, reactions become too slow. Under extreme salt stress, membranes and proteins struggle. Mars may produce combinations where every individual term sounds promising until the whole environment is assembled. Now this is the trap in the phrase liquid water. On Earth, those two words feel almost magical because they so often point toward life. On Mars, they can mislead us. A brine can be liquid because it is loaded with salt. That same salt can pull water away from cells and make the environment harder, not easier. So we need to ask a harsher question. Not whether water can avoid freezing for a moment, whether that water is available enough, warm enough, and stable enough for biology to use. Now brines also force us to think about time. A liquid film that appears briefly before freezing or drying may be chemically interesting without being biologically useful. We can imagine life enduring long dry periods. Earth gives us examples. But endurance is not the same as growth, repair, and metabolism. A Martian brine has to offer more than a momentary escape from freezing. Now we should keep our own intuition under control here. We hear liquid and we want to move the answer toward life, but on Mars, we have to ask what the liquid is doing to the cell, as much as what it is doing for the cell. So we come back to the same test. We need water that biology can use, not just water that physics can briefly keep unfrozen. That's why brines belong in the middle of the story, not the footnotes. They teach the viewer to distrust the easiest slogan before the final answer arrives. The poles are the most obvious ice on Mars, and that can make them misleading. From a distance, polar caps look like the natural answer to an under-ice question. They are vast and bright. They are layered and water-rich in a way the red plains are not. They hold climate history. They show that Mars has not lost every frozen reservoir. They give the eye a place to rest when the word ice appears. Yet abundance is not habitability. The polar environment adds severe cold and difficult access. Seasonal light limits matter too, so does a strong archive bias. A place can be excellent for preserving climate layers and still be a poor refuge for active cells. The poles matter, but their main lesson may be how easily water-rich scenery can outrun biological usefulness. The polar caps are the most obvious ice on Mars. They are vast, they are beautiful. They store climate history in layers. They show that water and carbon dioxide ice shape the planet season after season, but quantity is not habitability. The poles are cold. Sunlight is seasonal and low angle. Access is difficult. A rich archive can be poor habitat. The caps may tell us how Mars changed, while still failing as the best place for active modern life. The poles test our instinct for scale. They are the most visibly icy parts of Mars. They hold layered records. They change with the seasons. They make the planet look less dry than the red desert image suggests. But big ice is not automatically useful ice. A polar cap can preserve climate history beautifully while giving living cells almost nothing. Extreme cold slows chemistry. Seasonal darkness interrupts light. Low sun angles limit energy. Deep layers may be protected, but also sealed away from the conditions that would make liquid water and metabolism plausible. So the polar question has to be narrowed. Are we looking for a climate archive or an ancient preservation site? Are we looking at a transient surface process, or are we looking for an active modern habitat? Those are different goals. A mission built to read climate layers might succeed brilliantly without saying much about living cells. A mission searching for extant life would need a local exception inside an environment that is mostly too cold and too seasonal. The poles remain essential because they teach us Mars history and water storage. They may also preserve materials that matter for astrobiology, but their strength is not the same as the dusty ice doorway. Their abundance can distract from the tighter requirement: usable water, usable energy, and interpretable evidence in the same place. The largest ice deposits may be the best memory of Mars, not the best living niche. The poles also test our instinct for scale. Big ice feels more promising than small ice. More water feels better than less water. A cap that can be seen from orbit feels more important than a thin, dirty layer on a slope. But biology does not rank habitats by visual scale. It ranks them by usable conditions. The poles can be too cold for the kind of melting or metabolic activity the under-ice idea needs. They can preserve, record, and stratify without becoming friendly. In some ways, that makes them even more valuable scientifically. An archive can be priceless without being alive. Polar layered deposits may tell us how climate changed and how dust accumulated. They may show how ice advanced and retreated as Mars shifted its orbital tilt. Here is a profound story. It isn't necessarily the same story as extant life, so the poles stay in the trial as a warning. Do not confuse abundance with suitability. Do not confuse the biggest reservoir with the best niche. On Mars, the better hiding place may be smaller, warmer, dustier, and stranger. Warmer, so the poles stay valuable without becoming the easy answer. They hold records, reservoirs, and climate clues. For living cells today, they still have to overcome cold, darkness, seasonality, and the difference between preserving evidence and supporting metabolism. The polar caps are visually irresistible. They announce water from orbit. They mark the seasons. They hold layered deposits that can read like climate history written in ice and dust. If the video were only about where Mars keeps water, the poles would dominate, but a life search cannot rank by spectacle. The poles are cold in a way that matters chemically, not just emotionally. Low temperatures slow reactions. Seasonal darkness limits energy. Sunlight arrives weakly and at low angles. Some layers may be deeply buried. The ice can be valuable precisely because it is stable and inert, which is not the same as being alive. Here is the archive versus habitat distinction again. A polar layer can preserve atmospheric history and dust cycles. It can also record volatile exchange and climate shifts. It may hold clues that help reconstruct when Mars was wetter, colder, or more tilted. Those clues can strengthen astrobiology indirectly by telling us where water moved and how environments changed. But they do not automatically identify a modern refuge. If polar life were considered seriously, the best candidate would probably be a local exception rather than the cap as a whole. Perhaps a dusty layer that absorbs heat, perhaps an interface where salts concentrate, perhaps a place where seasonal processes create a brief liquid-like film, perhaps a buried contact that preserves ancient material. Each possibility is narrow. None follows simply from the amount of ice. The poles also raise access questions. Landing and power both become harder in severe polar settings. Thermal control, drilling, and sample handling add more difficulty. A mission must justify why the same resources should go there instead of to a mid-latitude deposit where light, access, and thermal conditions may be more forgiving. So the polar caps remain in the story as a necessary warning against scale bias. Bigger water reservoirs can be worse habitats. More obvious ice can be less useful. A place can be central to Mars climate science while sitting lower in an extant life ranking. That complexity is not a weakness. It helps the viewer understand why the answer is not simply go to the most ice. Mars asks for the right ice, not the most ice. The poles are where Mars looks most openly icy, but abundance can mislead us. A climate archive and a habitat are not the same thing. Layered deposits may preserve atmospheric history with extraordinary precision. Seasonal frost may move across the surface. Carbon dioxide and water ice may trade dominance in ways that reveal climate cycles. None of that automatically gives living cells a workable home. For modern life, the polar question is not how much ice exists. It's whether any part of that ice can combine shielding with usable water and energy. Low sun angles and extreme cold work against that combination. Seasonal darkness does too. Deep burial makes the problem harder again. The poles may be priceless for reading Mars history while still being poor candidates for active biology. The polar record can still shape the under-ice search indirectly. Climate layers tell us how Mars has moved water over time. Dust bands can reveal environmental cycles. Changes in orbital tilt can shift where ice is stable. If we want to know where a modern refuge might remain, we also need to know how ice migrated, retreated, accumulated, and was exposed. So the poles can guide the search even if they are not the preferred target. They help explain why mid-latitude ice exists, why some deposits are buried, and why the present distribution may be a snapshot of a changing planet. Mars ice is not only a substance, it's a history of movement. Now the poles remind us that more water is not the same as better habitat. The polar caps are enormous compared with a thin, dirty layer. They are also cold, seasonal, and difficult to read as living environments. We should value them first as archives. They store climate history. They record changes in dust and ice. They may preserve signals that open surface chemistry would destroy. But preservation and metabolism are different stories. A freezer can protect evidence beautifully, while offering almost nothing to a living cell today. Now look at the difference between scale and usefulness. The polar caps dominate maps because they are large. They shape the planet's climate story. They hold layers that can be read almost like pages in a frozen archive. But biology does not reward size by itself. A vast cold deposit can be less useful than a thin, warmer margin if the smaller place has water that moves, chemistry that exchanges, and energy that arrives at the right depth. So the poles remain essential to Mars science. They may hold evidence we badly want. They just do not automatically become the most likely refuge for life alive today. Whilst it's just true the day that history matters because long-term stability and repeated environmental windows may be more important than sheer volume. If sunlight becomes the problem, the search has to ask what replaces it. Deep below the surface, Mars would be better shielded from ultraviolet light, particle radiation, oxidation at the ground, and daily temperature swings. That makes the deeper subsurface attractive for a different reason than dusty ice. It does not depend on a delicate balance of sunlight and shallow protection. It asks whether water rock chemistry could provide energy in the dark. The price is distance from evidence. We do not know enough about where usable water persists, where chemical gradients remain strong, or how accessible those systems are. Deeper rock may be the safer refuge and the harder one to prove, moving the life question from a visible ice story into a drilling, contamination, and inference problem. If sunlight becomes impossible, chemistry has to carry the story. Earth has deep subsurface ecosystems that live without sunlight, using chemical gradients and water-rock reactions. That makes the Martian deep subsurface one of the most serious ideas in astrobiology. Mars may have had water-rock reactions and redox gradients. Radiolysis could add another source of chemistry, perhaps with hydrogen in protected settings. But each word there hides uncertainty. Where is the water now? Is there enough heat? Are the gradients active or ancient? Could we reach them without turning the sample into an engineering artifact? When depth removes sunlight, chemistry has to become the engine. That's not a weak idea. On Earth, deep microbial communities live with no daylight, using hydrogen, redox gradients, minerals, gases, radiolysis products, and water-rock reactions. A protected Martian subsurface would avoid many of the surface penalties that make shallow life so difficult. But protection is not the same as proof, and chemistry is not the same as access. Mars may have the right kinds of reactions in some settings, yet we do not know where they remain active today. Water may be frozen or isolated. It may be too saline, or simply too sparse to help, or too deep. Heat flow is limited compared with Earth. Chemical gradients may exist, but slowly and unevenly. The deep subsurface also pulls the video away from its ice anchor, unless we keep the connection clear. Ice can cap and preserve a deeper system. It can also feed it, or mark where the system once moved. But the deeper we go, the more the question becomes about water rock chemistry rather than sunlight under ice. That may be scientifically serious, but it is harder for missions and harder for evidence. A shallow, dusty layer might be sampled by a specialized lander. A deep, chemically powered refuge might require drilling beyond current life detection capability. So this candidate may rank high for shielding and low for testability. The deeper answer may be more plausible in one sense and less testable in another. The deeper subsurface is where the question becomes less visual and perhaps more biologically serious. On Earth, much of life is not waiting for sunlight. Microbes live in rock, groundwater, and deep fractures, drawing energy from chemistry. That possibility matters for Mars because sunlight is exactly what many protected places lose. Water-rock reactions can generate chemical gradients. Radiolysis can split water molecules and create reactive species. Serpentinization-like processes can produce hydrogen in the right geological settings. Redox couples can provide energy if the environment keeps them out of equilibrium. These become not fantasies, they are known astrobiological ideas, but the evidence for modern Mars is indirect. We do not have a map of living deep habitats. We do not know where liquid water persists in useful forms. We do not know whether chemical gradients remain active enough. Mars has lower heat flow than Earth. Its crust is old and cold. Its deep promise comes with deep uncertainty. The practical problem is severe. A shallow ice layer might be sampled by a specialized lander. A deep chemically powered habitat might require drilling far beyond current Mars life detection missions. The most protected place may be the least reachable place. Here is not just inconvenient, it shapes what we can know. So the deeper subsurface remains a serious but distant possibility. It may solve radiation better than shallow ice, but it replaces the light problem with a chemistry problem and the access problem with something much harder than a scoop or shallow drill. The deep subsurface is where Mars becomes less like a photograph and more like an inference. We cannot simply point to a bright scarp or polar cap and say, there. The evidence would come through geology, chemistry, thermal models, magnetic and mineral history, and analogues from Earth's deep biosphere. On Earth, deep life changes our intuition. Sunlight is not required everywhere. Microbes can live from chemical disequilibrium, drawing energy from hydrogen, sulfur, iron, methane-related chemistry, radiolysis products, and water-rock reactions. Rock can be a habitat when water moves through it and chemical gradients persist. That matters because depth is the cleanest shield from Martian radiation. Mars may have had settings where these processes operated. Ancient water-rock reactions are recorded in minerals. Serpentinization-like pathways can produce hydrogen under the right conditions. Radiolysis can create reactive species from water. Redox gradients can, in principle, feed metabolism. The scientific case is not silly. It's one of the more serious ways to imagine life without sunlight. The difficulty is present tense. Are the ingredients still connected today? Is liquid water available anywhere useful? Are the reactions active or only preserved as ancient signs? Is the heat flow enough? Are the gradients strong enough? Could organisms persist through long intervals of isolation, cold, and limited nutrients? Every promising word carries a hidden measurement. Detection then becomes the hardest part. A deep refuge might be the best place biologically and the worst place operationally. Current Mars missions are not built to drill kilometers into sterile, controlled, geochemically complex settings. Even shallow drilling is hard. Deep drilling multiplies contamination and heating problems. It also turns engineering and interpretation into one tangled challenge. This candidate therefore changes the emotional shape of the answer. The most protected habitat may not be the one we can test first. A less perfect shallow ice site might be scientifically more useful because it can be sampled cleanly. A better biological target that remains inaccessible can keep the question alive without giving us a near-term answer. So the deep subsurface should be treated as a serious possibility, not a dramatic reveal. It widens the ranking and reminds us that life does not require sunlight. Then it asks whether a hidden chemical world can ever become evidence rather than inference. When sunlight fails, chemistry becomes the alternative. Earth proves that deep life can live without the sun. Microbes can use hydrogen and redox gradients in places that never see daylight. Minerals, gases, and water rock reactions can become part of the same energy story. That idea matters for Mars because depth solves the radiation problem more cleanly than shallow ice ever can. But Mars does not automatically inherit Earth's subsurface richness. The crust may be cold, water may be locked away, heat flow may be limited, chemical gradients may exist, but slowly, unevenly, and beyond reach. A deep habitat could be more plausible biologically and less testable scientifically. The better shelter may also be the darker mystery. A deep chemical refuge would also change what evidence looks like. We would not expect a sunlight-driven signal. We might look for mineral alteration or gases out of equilibrium. Isotopic patterns could matter too, especially if organic distributions connect back to water-rock reactions. Each of those signals can be biological or geological, so context becomes everything. The deep case also has a time problem. A subsurface environment may have been more active in the past than it is now. It may preserve traces of a once habitable system while offering little present metabolism, or it may remain slowly active in pockets we cannot yet reach. Distinguishing those possibilities is difficult from orbit and difficult from shallow landers. Now, if we let go of sunlight, the search changes character. The ice layer in the thumbnail becomes a doorway into a deeper question about chemical energy. We know Earth has life that does not depend on daylight. We know rock and water can create chemical gradients that organisms exploit. That makes the deeper Martian subsurface serious, not silly, but it also makes the evidence harder. We cannot see the habitat directly from orbit. We may not know where the right fracture or water-rock interface is. And we cannot casually drill until something interesting appears. Now, this deeper possibility also changes the kind of life we are imagining. Photosynthesis becomes less important. Slow chemistry becomes more important. The pace of any ecosystem, if one existed, might be almost unimaginably low. We should be careful here. Slow does not mean impossible. Earth's deep biosphere shows that life can persist where energy arrives in tiny amounts. But tiny energy budgets make detection hard because biology leaves weaker, slower, more ambiguous traces, so the deeper case may be scientifically stronger in shelter and scientifically weaker in access. That trade-off is exactly why Mars refuses the simple answer. Now there is a second problem with depth. The deeper target may not announce itself with a clean surface sign. A buried chemical habitat could sit below ordinary-looking ground. We might need indirect clues, minerals that remember water, fractures that could have carried fluids, or thermal models that point to the least impossible places. That makes the search slower, but also more honest. So the deep subsurface is a reminder that the best answer may not be the first answer we can test. Mars may keep its most protected possibilities behind the hardest evidence wall. Earth keeps offering examples that feel almost too encouraging. Microbes live in Antarctic ice, salty lakes, permafrost, deserts, deep rock, and subglacial systems. Dark grains on ice can create melt pockets. Life can slow down and wait. It can repair damage. It can exploit tiny chemical gradients when the setting allows it. These analogues are useful because they show what biology can do at the margins when a planet is otherwise harsh. But analogues are maps, not verdicts. Earth has a thick atmosphere, higher pressure, active hydrology, a connected biosphere, and a long biological inheritance that keeps seeding extreme places. Mars has a different radiation history and different chemistry. Its water activity is different too, and it may have no living source population at all. The analogy can widen imagination, but it cannot carry the burden of proof. Earth analogues are seductive because life here is astonishingly resourceful. Microbes live in Antarctic ice. They live in permafrost. They survive in brines. They persist in deserts that feel almost Martian by Earth standards. Cryoconite holes show how dark grains on ice can create tiny watery ecosystems. But Earth has an atmosphere, a biosphere, a different pressure regime, different chemical cycling, and a history soaked in life. Earth analogues expand imagination. They do not transfer probability wholesale to Mars. Earth analogues are useful because they widen the search without settling it. Antarctic cryoconite holes show dust and sunlight working together inside ice. They show melt, but only under Earth's rules, and microbes interacting in small systems. Permafrost shows persistence through long, cold intervals. Hypersaline lakes show that some organisms tolerate extreme salt. The Atacama helps scientists test instruments and ideas in harsh dryness. Those examples matter. They stop us from declaring a marginal environment dead simply because it looks cold or salty. Dry and dark can matter too, but they do not automatically end the question. Biology can use strange margins when the rest of the planet gives it time and water. Nutrients matter. So does a history of dispersal. Then the analogy has to stop. Mars is not a colder Antarctica. Its pressure is lower, its atmosphere is thinner, its surface radiation is harsher, its oxidant chemistry is different, its water history is broken and intermittent. Most importantly, Earth analog sites sit on a planet already full of life. So microbes arrive with a biological inheritance Mars may never have had. The best analogs therefore act like training grounds. They help us ask what a signal might look like. They show how instruments can be fooled, and they remind us that contamination and small habitats have to be studied together. They do not assign Mars a probability by copy and paste. Earth keeps the search honest. Possible does not mean proven. The best use of analogs is disciplined imagination. Antarctic cryoconite holes show that dust and ice can interact with sunlight. Microbes can join that system when melt lasts under Earth conditions. Permafrost shows that life and biological material can persist through long cold periods. Hypersaline environments show that some organisms tolerate salt far beyond ordinary limits. The Atacama helps test instruments and ideas under extreme dryness. Each analog gives a piece of the possibility map. None gives the whole Mars answer. The pressure on Mars is lower. The atmosphere is thinner. The ultraviolet environment is harsher. The oxidant chemistry is different. The history of available water is different. Earth analogs are still Earth ecosystems connected to a planet full of life. That does not make them useless. It makes them tools. They tell mission planners what signatures might survive, what instruments might fail, how contamination can move, and how life changes rock, ice, and chemistry in marginal settings. The correct sentence is simple. Earth proves life can exploit strange niches. It does not prove Mars has life in its strange niches. That sentence should sit behind every analogy in this video. Analogs become a discipline, not a shortcut. We use them to imagine mechanisms, test instruments, and recognize false confidence. Then we return each lesson to Martian pressure, radiation, chemistry, water history, and contamination risk. The best analogs do two opposite jobs. First, they make us less arrogant about where life can persist. Then they make us less careless about exporting Earth's success to Mars. Antarctic ice shows that cold environments can host biology when pressure and atmosphere cooperate. Seasonal energy and liquid microenvironments have to cooperate too. Cryoconite holes show that dust on ice can create little warm, wet systems where microbes gather. Permafrost shows long-term survival and preservation. Hypersaline systems show that life can adapt to salt. The Atacama shows that dryness can be severe without making every biological trace impossible. Those examples are powerful because they give mission designers mechanisms to study. How does life alter minerals? What organics survive? How does a tiny wet interval change chemistry? How do instruments behave in salty or dusty settings? What changes when the same sample is cold, dry, or both? How does contamination move through ice and drill hardware? What happens when sample tubes and field procedures become part of the evidence chain? Analog work is where many mistakes can be found before Mars makes them expensive, but Earth remains the wrong planet in crucial ways. Its atmosphere gives pressure and shielding. Its water cycle refreshes environments. Its biosphere spreads organisms into margins again and again. Its chemistry has been processed by life for billions of years. Even the harshest Earth analog is surrounded by a living planet, and that background changes everything. Mars may have had life once, or it may not. If it did, life may not have spread everywhere. If it did not, then a physically habitable niche could sit empty forever. Earth analogues cannot distinguish those histories. They can only show that certain mechanisms are possible for biology somewhere. That's why analogues should never become proof by atmosphere. A cryoconite hole on Earth can show how dust and ice interact with sunlight. It can show when melt becomes possible. It cannot tell us that Martian dusty ice contains organisms. A hypersaline lake can show the limits of salt tolerance. It cannot tell us that perchlorate-rich Martian brines are usable. A deep Earth mine can show chemistry-powered ecosystems. It cannot tell us where Mars keeps active gradients now. Used well, analogues are humility machines. They prevent dismissal and overclaiming at the same time. They give us better questions, cleaner instruments, and stronger skepticism. Earth analogues are powerful because they let us practice humility in both directions. They warn us not to declare a cold, salty, dark place dead too quickly. Life on Earth has used glacier surfaces, permafrost, hypersaline lakes, deep rocks, deserts, and subglacial systems. Biology can be patient and opportunistic. Then the same analogues warn us not to smuggle Earth into Mars. Our planet has a thick atmosphere, active water cycles, plate tectonics, global biology, and a history soaked in life. Mars has lower pressure and stronger surface radiation. Its oxidants are different. Its long record of dryness changes the meaning of every analogue. The analogy opens the question, it does not answer it. The language of analogues should stay exact. An analogue can be similar in one variable and different in 10 others. Antarctic ice may match cold but not pressure. The Atacama may match dryness but not radiation history. Hypersaline lakes may match salt stress but not temperature or atmospheric loss. Deep mines may match darkness but not Martian geology. Good analog science chooses the comparison deliberately. It asks one question at a time. How does an instrument respond to salts? How does organic material survive dryness? Then, only after that, how do drilling and small melt pockets change the chemistry we think we are reading? The analogy is powerful only when we know which part is being compared. That precision protects the viewer from a false emotional leap. Life survives somewhere harsh on Earth. Therefore, life probably survives somewhere harsh on Mars. The truth is more demanding and more useful. A disciplined analog also helps with humility about instruments. Before a sensor goes to Mars, scientists can ask how it behaves in cold brine, dry dust, ice mixed with minerals, or samples carrying tiny biological residues. They can learn which signals survive storage, which vanish during handling, and which appear only because the method itself introduced them. The analog site becomes a rehearsal for doubt. That rehearsal matters because Mars will not give us a second Earth laboratory. We cannot send teams of field scientists to walk around the suspected layer with coolers, sterile tents, and backup instruments. We send a machine, and the machine must be designed around lessons learned elsewhere. Earth analogues make that machine less naive. Now analogues work best when we use them with humility. Antarctica can show us dirty ice that melts around dark grains. Permafrost can show us long survival in frozen ground. Deserts can show us how life retreats into tiny protected spaces. But every analogue also carries Earth with it. Earth has pressure. Earth has a thick atmosphere. Earth has biology constantly arriving from somewhere else. So the analogue does not answer the Mars question. It trains our imagination. It shows us what to test, what to measure, and what not to assume. Now the best analogues also teach discipline in instrument design. Before we trust a sensor on Mars, we can test it in cold ice and salty films. We can also test it in dry soil, where biology is sparse enough to challenge the method. But we should listen to the negative results too. Some Earth analog sites are harsh enough that life is patchy, faint, or absent in places that look promising from a distance. That is useful because Mars may be even less forgiving, so analogues give us a practice ground. They do not give us a verdict. They help us avoid both mistakes, assuming Mars is dead too quickly, and assuming Earth has already answered for it. So analogues are not side stories. They are how the under-ice search becomes testable before the drill ever touches Mars. A plausible hiding place is still not a discovery. At some point, the question has to leave habitat physics and become evidence. What would count as a living Martian signal rather than an interesting chemical pattern? Organics alone are not enough. Texture alone is not enough. A gas measurement or an isotope ratio can mislead. So can a possible cell shape or a wet-looking mineral pulled out of context. This is where the story becomes more demanding, not less. A modern biosignature would have to survive the ordinary explanations first. Chemistry can imitate life. Old preservation can look newer than it is. Contamination can make Earth appear inside a Martian sample. The more extraordinary the claim, the more carefully the evidence has to stack. A habitable layer would not be enough. We would need evidence. Organic molecules could matter, but organics can be non-biological or ancient. Isotopes can hint at metabolism, but abiotic processes can fractionate isotopes too. Cell-like shapes can mislead, gases can come from geology. Chemical disequilibrium can be suggestive without being decisive. The bar for extant life is a ladder, not a button. Context and controls matter, so do blanks and repeat measurements. Independent instruments matter too, especially when the contamination history is hard to untangle. A single exciting molecule cannot carry the claim by itself. A plausible habitat only earns the next question. What would count as evidence? Organic molecules would be exciting, but organics can arrive by meteorites or form abiotically. Isotopes can hint at metabolism, but non-biological processes can fractionate them too. Cell-like shapes can be minerals. Gases can come from geology. Chemical disequilibrium can invite a biological reading without demanding one. So, proof has to be layered. A serious claim would begin with site context and clean controls. It would have to repeat where the geology says it should repeat. Then independent instruments would need to point toward the same interpretation without sharing the same weakness. One lonely signal would not be enough. The stronger case would come from convergence. Chemistry and structure would point one way. Context and controls would point there too. This matters especially under ice, because preservation and activity can look related while meaning different things. Ancient organics in a protected layer would matter. They would not automatically prove living cells today. A modern metabolic signal would matter even more, but it would need to be separated from abiotic chemistry and anything we brought from Earth. The viewer deserves that standard before the final answer. The question is not only where life could hide, it's how we would separate life from chemistry. We would also have to keep old preservation and contamination from masquerading as the same thing. The hard part may not be naming a habitat. It may be proving the signal is life. Imagine the most tempting result. A drill reaches a protected icy layer and instruments detect organics. The sample chemistry looks unusual. A microscope or gas sensor adds another hint. The story would race around the world in minutes. Science would have to slow down. Organics can arrive by meteorites or form through non-biological chemistry. Isotopic patterns can have abiotic roots. Cell-like shapes can be mineral textures. Methane and other gases can have geological pathways. Even chirality, the handedness of molecules, would need context and controls. Each signal becomes stronger with others, but none is magic alone. The question is not whether one measurement is exciting. The question is whether a whole pattern survives competing explanations. Does it appear in the right geological context? Does it repeat in nearby samples? Do blanks stay clean? Do independent instruments agree? Does the chemistry fit active metabolism rather than ancient preservation? Here is why a serious Mars life documentary must end near standards of proof. The viewer deserves more than the hiding place. They deserve to know what would actually count. So proof standards become part of the habitat ranking. A site that cannot produce interpretable evidence may remain scientifically interesting but unsatisfying. The best target is not only plausible, it is one where a clean, repeated contextual signal could survive doubt. A discovery claim would not begin with a press conference. It would begin with a chain of evidence that survives being pulled from every direction. Under Mars ice, that chain has to be especially strong because the environment can preserve old material, alter chemistry, and invite contamination all at once. Start with organics. Organic molecules would be important, but Mars receives organics from non-biological sources and can produce some through abiotic chemistry. Radiation and oxidants can also break them apart or transform them. So the question is not simply whether organics appear, it is whether their pattern fits the depth, the minerals, and the mission's own contamination record. Move to isotopes. Biology can leave isotopic patterns, but abiotic processes can also fractionate isotopes. A suggestive ratio becomes stronger only when it fits the context and lines up with other evidence. Move to shapes. Tiny cell-like forms can excite the eye, but minerals can mimic cells. Move to gases. Methane or hydrogen can provoke interest. Oxygen can too, especially if the wider chemistry is out of balance. Yet geology can produce surprising chemistry too, so the standard is convergence. First, the site itself has to make biological sense, protected enough to preserve a signal, and active enough for water and energy to matter. Then the chemistry has to fit that setting instead of floating free as one exciting molecule. Finally, the same pattern has to survive repetition and clean controls. If independent instruments agree after that, the case starts to become something stronger than a coincidence. The highest bar belongs to extant life. Ancient biosignatures would be extraordinary, but modern metabolism asks for stronger evidence, something active or recently active, not merely preserved. A living cell, a metabolic pattern, or a repeatable chemical disequilibrium would need to be protected from the obvious alternative explanations before it could carry the claim. This makes the final answer more satisfying, not less. We are not lowering the drama by demanding standards. We are protecting the drama from collapsing into a false positive. Modern Martian life would be one of the largest scientific discoveries in history. It deserves a standard strong enough to carry that weight. So when a future headline says possible biosignature, the trained viewer should ask better questions. Start with the sample context, then ask whether the controls stayed clean and whether geology can explain the pattern. Only after that does repetition become persuasive, because a repeated mistake can look like a repeated discovery if the mission does not understand its own fingerprints. Those questions are not cynicism, they are how curiosity becomes knowledge. The same standard applies to a negative result. If a mission samples one icy site and finds no life, Mars is not automatically dead. The site may have been wrong, the layer may have been missed. The instruments may have lacked sensitivity, the habitat may have closed long ago, the sample may have been altered during collection. Absence becomes meaningful only when the search is precise enough to say what kind of absence was measured. So evidence standards protect both outcomes. They stop weak positives from becoming myths, and they stop weak negatives from becoming premature endings. Proof has to be layered because Mars can imitate life in pieces. Organic molecules can be delivered or made without biology. Isotopic patterns can look suggestive and still have abiotic roots. Even a cell-like shape can be a mineral trick. Chemical disequilibrium may invite a biological reading, but it cannot carry the claim alone. A serious claim would need convergence. The site would have to make sense. The instruments would have to show their own sample path was clean. The chemistry would have to repeat in a pattern rather than appear as one lonely signal. Ideally, independent instruments would point in the same direction. The bar sounds high because the prize is high. Modern Martian life would change science forever. A weak false positive would damage the search for years. A false positive would not merely be embarrassing, it would distort mission priorities and public trust. Funding would follow the distortion, and so would the interpretation of later data. Scientists would spend years disentangling whether Mars had spoken or whether our instruments, assumptions, or contamination controls had failed. That's why caution around biosignatures is not a lack of imagination. It's protection for the discovery itself. A strong positive would probably feel frustrating at first because it would invite more tests instead of immediate certainty. Repeat the measurement where the geology predicts it should repeat. Check the clean controls before celebrating. Then ask whether non-biological chemistry can reproduce the pattern. The process would be slow because the claim would be enormous. Now keep one thing in view as we weigh any future signal. We are not asking whether one measurement looks biological in isolation. We are asking whether the whole setting can carry that interpretation after ordinary chemistry, old preservation, and spacecraft history have been tested hard. A protected layer might preserve organics beautifully and still say nothing about living cells today. A chemical pattern might look metabolic until the minerals, depth history, or controls explain it another way. So the proof has to connect the signal to the place, not just to our hopes. Evidence under Mars ice follows one hard rule. A claim becomes stronger only when the local context is clear, the pattern repeats, and clean controls agree with instruments that work independently. Not one dramatic molecule, not one seductive image, a pattern that survives doubt. Now the proof problem becomes sharper when we separate ancient life from living life. A sample could contain old organic material and still tell us nothing about a cell alive today. It could preserve chemistry from a wetter Mars and still come from a dead modern niche. We need that separation because the title asks about life hiding now. Not simply whether Mars was once habitable, not simply whether carbon-bearing molecules survived. The modern question demands evidence of present or very recent biological activity, so the strongest claim would not rest on one sign. It would be a pattern. Location and chemistry would point one way. Texture, controls, and repetition would point the same way, while non-biological explanations lose strength. Where that's the right pace. The first possible signal under Mars ice would not be the end of the story. It would be the beginning of the most careful argument planetary science has ever had. The final obstacle is us. The most interesting sites are not only scientifically delicate, they are operationally delicate. A drill can carry Earth organisms, a warm instrument can alter ice, and once a sampling system enters a narrow protected zone, the act of reaching it can change the thing we are trying to understand. Planetary protection is therefore not bureaucratic caution pasted onto the end of the story. It is part of the evidence. If the sample path is not clean, the site is not controlled, and uncertainty is not handled honestly, a possible discovery can collapse into a question about our own fingerprints. Mars may be hard to test because the best hiding place is also the easiest place to contaminate. Planetary protection can sound like paperwork until you imagine the sample. A drill touches ice that may be one of the best modern habitats on Mars. The drill has a history. The spacecraft has materials and residues. It may carry heat, microbes, and handling pathways into the place we are trying to read. If any of those enter the habitat, the experiment changes. Forward contamination is not a public relations problem. It's a scientific problem. If Earth biology enters a possible Martian niche, later evidence becomes harder to interpret. The mission could create the signal it was designed to detect, or destroy the fragile pattern it needed to preserve. Contamination changes the under-ice question because the target may be small, slow, and fragile. If the best candidate is only a thin layer or a salty film along an ice-rock contact, then a drill is not just a tool, It becomes part of the environment. Heat can alter ice. Mechanical action can smear material between depths. And once spacecraft residue enters the sample path, even a clean mission has a history that must be explained. That history matters most when the signal we seek may be faint, so planetary protection is not a bureaucratic afterthought. It's how the result keeps its meaning. Sterile hardware matters. Witness plates and blanks matter, but the deeper point is larger than any one procedure. The mission has to leave a record clean enough that later scientists can subtract ourselves from the measurement. The irony is sharp. The more interesting the habitat becomes, the more careful our touch has to be. A site promising enough for modern life may also be sensitive enough that impatient sampling would make later interpretation almost impossible. Curiosity has to become restraint before it can become knowledge. The search itself becomes part of the experiment. Planetary protection is the final gate because Mars life, if it exists, may be sparse and slow. It may also be fragile in ways our machines cannot easily notice. Earth organisms are adapted to Earth, but some are astonishingly hardy. Spacecraft are cleaned carefully, yet cleanliness is not the same as perfect absence. The closer a mission moves toward a potentially habitable niche, the more demanding the standard becomes. A drill does more than remove material. It adds heat. It creates fractures. It can smear material between layers. After that, residues and terrestrial molecules become part of the evidence problem. Even the act of approaching the best habitat can make the evidence harder to trust. We are not looking at a conspiracy boundary. It's the opposite. It's a truth-preserving boundary. If we ever find a signal under Mars ice, the discovery will only matter if the chain of evidence is clean enough to survive doubt. Planetary protection protects Mars, but it also protects the meaning of the result. That gives the ending its tension. The places we most want to test may be the places we should touch last, with the best tools, the strictest controls, and the least impatience. Curiosity has to become restraint before it becomes knowledge, so planetary protection becomes the final constraint rather than an appendix. A mission that cannot control its own fingerprints cannot answer the under-ice question. The cleanest search may be slower, but speed is useless if it ruins meaning. Planetary protection becomes most important exactly where the science becomes most interesting. If a site is clearly exposed and dry, contamination still matters, but the biological stakes are lower. If a site might contain usable water under cover, then every Earth molecule carried there becomes part of the story. A spacecraft is never just metal. It has manufacturing history. It has clean room history. Residues come with it, and so may traces of biology even after serious cleaning. Engineers work hard to reduce those risks. The point is not that missions are careless. The point is that the best Martian target may demand a level of care that shapes the mission from the beginning. Drilling adds its own complications. A bit can heat the ice and change its state. It can smear material from one layer into another. It can open a protected layer to conditions it has not felt before. A sample can become a mixture before the instrument ever sees it, and that mixture may tell us more about the drilling than about Mars. Controls are how scientists fight that confusion. Witness plates record what the spacecraft brought. Blanks reveal contamination in instruments and reagents. Then the rest of the mission record has to do the same job: protect the sample path, control heat, and let later teams reconstruct what happened. These details sound procedural until we imagine trying to defend a possible life detection without them. This also creates a moral and scientific restraint. If Mars has a rare modern habitat, we should not be the force that damages it before we understand it. Planetary protection protects Mars as a world, but it also protects the answer from us. A contaminated discovery is not a discovery with an asterisk. It may become no discovery at all. The tension at the end is therefore not fear of exploration. It's better exploration. Go carefully enough that the result can be believed. Sample slowly enough that the habitat is not turned into an artifact. The mission has to make both outcomes meaningful, a positive signal that survives doubt and a negative result that still teaches us something. That restraint is the opposite of anti-science. It's science mature enough to know that touching the unknown changes it. One full hedge protection can sound like paperwork until we imagine the sample. A drill enters ice that might be rare and protected. The drill carries history from Earth. Residues and dead biological fragments may be enough to confuse a faint signal, even when engineers have done their work carefully. Then the act of drilling adds heat and changes the exposure of the layer. Sampling becomes part of the environment being sampled, so caution is not timidity. Caution protects meaning. If we ever see a possible biological signal, we need to know it belongs to the Martian setting rather than to our hardware or handling. The clean search is slower, but it is the only search that could give an answer worth believing. The contamination problem also gives the ending its human edge. We are part of the experiment whether we admit it or not. Our machines carry our planet's chemistry. Our desire for an answer creates pressure to touch the most interesting places. Our history of exploration shows that arrival is never neutral. A mature Mars program has to carry two ambitions at once. It should be bold enough to seek protected habitats and restrained enough not to spoil them. It should design instruments sensitive enough to notice faint biology and controls strong enough to prove the signal did not come from the instrument itself. It should accept that some places may need to wait until our tools are cleaner. That patience is not a retreat from the question. It's the only way the question can remain answerable. Imagine the alternative. A mission rushes into a protected icy layer and returns an ambiguous organic signal. The public hears possibility, scientists hear a damaged sample path and a missing history of controls. Years of argument follow, but the original site can no longer be restored to its untouched state. The opportunity was not used, it was consumed. A cleaner mission may feel less cinematic, but it gives the future more room. It lets a positive result become stronger and a negative result become informative. In a search this delicate, restraint is not the enemy of discovery. Restraint is the structure that lets discovery survive. Now keep one thing in view as we approach the sample path. The question is not only whether Earth organisms could survive on Mars for a while. The question is whether any Earth material carried by the spacecraft could confuse a signal faint enough to matter. A drill does not enter the ice as a neutral observer. It brings heat and foreign surfaces. It carries residues from its own path. If those touch the wrong layer, the mission may no longer be reading Mars alone. It may be reading Mars mixed with our own arrival. So the final rule of the search is procedural as much as biological. The cleaner the sample path, the more meaning a result can hold. Not because paperwork discovers life, because without a trustworthy path from ice to instrument, even a real signal may become impossible to defend. Now this is also why the most interesting sites may face the strictest rules. A place with possible liquid water or usable brine is exactly the kind of place where terrestrial microbes, if carried there, would matter most. That can feel frustrating. We may want the drill to go straight to the best target. But the better the target becomes, the more careful the mission has to be about every surface that touches it. So the final constraint is not only scientific, it is ethical in a narrow, practical sense. We should not damage a possible Martian habitat before we know whether it is one. Now the best mission would treat contamination records as evidence, not paperwork. Every clean surface would matter. Witness plates and blank samples would matter. Even the thermal log would become part of the final interpretation. We would not ask only what the instrument saw. We would ask how the sample reached the instrument, what touched it, and whether the same pattern appears where contamination should not be present. That structure also helps if the answer disappoints us. A clean negative result can still narrow the map, remove a weak candidate, and make the next mission smarter. A messy result only leaves doubt behind. So could life be hiding under Mars' ice? The honest answer is yes, but only in a narrow and conditional sense. Not as a hidden world, not as a confirmed biosphere, not as a secret waiting just below the dust. The best case is smaller than that, and more difficult. We have followed the surface first because it explains the whole problem. The ground Mars shows us most easily is punished by radiation and dryness. Unstable water and reactive chemistry make it harsher still. If active life exists today, it probably needs shelter, and ice is the most serious shelter Mars offers near the surface. It can block some radiation, it can preserve delicate evidence, it can hold dust, salts, and minerals in contact. Under special conditions, it may help water appear briefly or locally enough to matter, but a shelter is not a home by itself. Dirty ice gives the cleanest doorway because it keeps the central trade-off visible. Too shallow and radiation wins. Too deep and light disappears. Add salts and liquid water may remain liquid while becoming less useful for biology. Move into buried glaciers and protection improves while energy becomes harder. Move toward the poles and the ice grows vast while the conditions become severe. Move deeper still and chemistry may replace sunlight, but the evidence becomes almost unreachable. So the strongest answer is not a place name, it is an overlap. A possible modern Martian habitat would need enough shielding to protect fragile chemistry. It would need water that is available, not just frozen or chemically locked away. It would need usable energy. It would need temperatures and salts that do not close the biological door. And it would need to last long enough for life to do more than merely endure a moment. Earth tells us this search is not foolish. Antarctic ice and permafrost show how inventive biology can be. Deep rock and salty margins widen the lesson. But Earth also warns us. Our planet is wet, protected, and already alive almost everywhere. Mars is not Earth with the volume turned down. It is another world with another history. That is why proof becomes the final wall. Habitability is not habitation. Organics are not automatically biology. A texture is not automatically a cell. Before we could claim modern life under Mars ice, the signal would need context, clean controls, and a contamination history strong enough to survive doubt. And that leads naturally to the next question for Genius Night Science. How would we know a life detection experiment had really found life? The Viking landers already forced that question once, and a future GNS documentary on the Viking life tests would be the direct next step. For now, Mars gives us something quieter and harder than a headline. It gives us a map of possible refuges, a few thin margins where ice may protect, water may briefly appear, and energy may remain long enough for chemistry not to close the door. And the same discipline will matter beyond Mars. Europa and Enceladus raised the ice question on a larger scale, with oceans hidden beneath shells rather than thin Martian layers. The details are different, but the lesson carries forward. Water creates a question, not an answer. If life is there, it will not be easy to find, and if we ever touch that place, we will have to arrive carefully enough to know the answer is Mars speaking, not us.